maybe a slight change of emphasis. So there's not been a lot of people talking from industry this last few days. I've enjoyed the workshop, and thank you very much to the organisers for putting together a really good session and allowing us some time to debate and discuss things. So I represent effectively an industry component of the supply chain should a quantum network be developed. And I think when I was approached to talk, I was mainly asked to talk about that topic, but I think in doing so, I should give a sense of what's happening in quantum diamond and some of the other areas we're talking about before talking a little bit about the challenges to scale the technology for markets yet to be clearly identified. So scaling, delivering diamond quantum solutions. So give a very brief introduction to quantum diamond. You've heard some of this before, beautiful talk from your Rashop at lunchtime, just before lunch. Then I'll say a little bit about some of the work we've been doing on color centers and their application, talking a little bit about one of the other applications driving quantum diamond, magnetic sensing, because that has some parallels and has some other pools for the material which this community can benefit from, but also it diverges at some points. And then to end the talk a little bit about how do we as a commercial organization think about this, what are the risks in scaling this technology, and how the ecosystem as a whole perhaps could work together to make sure that those risks are mitigated, and how that might work, and a few learnings from the semiconductor industry there, where I spent a large part of my life in the US a few years back. So quickly, diamond's engineering appeal. Many of you know something about its quantum properties, but diamond is also a very good conductor of heat. In fact, it's the best conductor of heat of any material. So believe it or not, the fact this video is happening, and hopefully you can see me and no interrupts, is actually in part of the internet backbone. There's a electrical to optical converter, and that's mounted on a piece of diamond because the power density going through that is such that you've got to keep it cool. So mounting on a piece of diamond allows the bandwidth we increasingly take for granted in the current age. So diamond's already playing a role in classical networks, more from a thermal management point of view, from a passive use of some of its properties. Optically, many of you know it's transparent from the UV all the way out to the far infrared, all the way out to the RF part of the spectrum. So high power lasers have been using diamond now for 20 years for pushing power densities up. But the emphasis today is talk a little bit about the quantum. So if you think about a host material for a quantum spin, naively you look at diamond, and actually diamond looks quite appealing. Short, stiff, rigid bonds. So basically your spin orbit interaction is very, very, very weak. T1 times can be very long. Your natural abundance of nuclear spins is very low because most of diamond is carbon-12, which has 0 nuclear spin. So unlike quantum dots, you're not dealing with a lot of nuclear spins in the material. So your T2 times can be quite long. And then on top of that, of course, you want long coherence times, you want low spectral diffusion, and ideally you'd like a transition that easily maps into existing telecoms infrastructure in the infrared. So we've been working on and investing and developing research in diamond for 60 years. And a lot of that in the first 30 years was all about understanding diamonds, natural diamonds properties. And in the last 30 years, really been emphasizing how we can use synthetic techniques to grow diamond and actually control its properties. And the technique we use that's helped unlock some of these applications you've heard about, and we hope will continue to unlock more, is a process called chemical vapor deposition. So for those unfamiliar to diamond in its crudest sense, it's a more akin to a semiconductor process for making material. We feed energy into a resonant chamber, shown here on the left. That energy heats up the gases. The gases in the simplest form are carbon containing, so methane and hydrogen. And if you like, the magic chemistry is the hydrogen, because you have a much cooler substrate than the plasma. The carbon precipitates out of this hot plasma on that substrate, both as sp2 graphitic phases and as sp3 diamond phases. But if the plasma is hot enough, you can produce an awful lot of atomic hydrogen, and that atomic hydrogen etches away the graphite, the sp2 phases, and by default leaves sp3 diamond. So for many, many years, people believed you couldn't grow diamond in this part of the phase diagram, relatively low temperatures and pressures, because it's a place where the local chemical kinetics beat the local thermodynamic conditions. So you can grow diamond at relatively low temperatures and pressures using chemical vapor deposition. The benefit then of this environment means that you can start to think about doping. You can control the purity. You can add impurities into the gas phase for doping. So we're going to talk a little bit about silicon and nitrogen in a bit. So we can add those deliberately into the plasma, and then and not quite MBE type control, but you can get layer by layer growth of these defects into the material, these color centers in the material. We've been developing this for 20 years, and that shows an example of a 6-inch wafer that we use in a thermal application. So in principle, it's a scalable process that you can deposit over relatively large areas. It's fair to say, though, the quantum community has pushed us to the extremes of our understanding of this process. The need for nanoscale and sub-part per billion level of control of impurities has really been a challenge, and so far, Diamond's good progress been made, and we've hit something. We met many of those challenges. And the things we have to think about: gas phase, surface processes, quality of the surface, and it's all those things together. As a material grower, you have to put together and solve the matrix of bonds. So quickly go through the two most common defects being explored right now for quantum networking and an array of other quantum diamond devices that we're talking about at the moment. It's nitrogen-vacancy defect. Carbon atom associated by nitrogen next to a neighboring vacancy. It has an electronic spin associated with that. That electronic spin can have very long T1 times. It can be minutes at room temperature. And T2 can approach T1, especially if you take the natural abundance carbon-13 out of the material and go to isotopic purity. One of the challenges of the nitrogen vacancy defect, however, is actually it has a very broad emission, with a lot of emission in this phonon sideband. So it has a pretty low Debye-Waller factor. And that can be a challenge when you want to get efficient coupling of photons away from these spins in the material. Silicon vacancy in the last couple of years have been explored by a number of groups, and Jorg talked about some of that, and some lovely work from Natalie in Princeton, Leon in Princeton, and the Harvard teams. And that's beginning to increasingly leverage the neutral charge state of the silicon vacancy defect. It's a defect that hadn't been explored that much until the last 4 or 5 years. And one of the nice things about it is it emits at 950, so it emits in the near infrared, much closer to the telecoms wavelengths. Again, while you have to resort to cryogenic temperatures, in this case, it can have very long T1, T2 times, with the benefit of actually better optical properties. So not only is the emission closer to is in the NIR, it's also actually a much narrower transition. So that's one of the reasons why that's being explored at the moment. So switching quickly back to the NV and talking a little bit about the flavor of the work that we've been heavily involved with over the last 5 or 6 years. As many of you know, this nitrogen vacancy defect, you can spin polarize at room temperature by shining a green light on. These one states will go up to 1, but some of them will relax back via this singlet state and preferentially populate the 0 state. So you can go around that cycle a few times and actually optically spin polarize the 0 state. And then with an RF source around 2.8 gigahertz, you can cycle those transitions between the 0 and 1 and produce a superposition state. You can then come back along and interrogate that system, shine another green photon, throw another green photon at it, and actually measure the intensity coming out. And depending on whether it's in the 0 state where it's brighter, when the 1 state is darker. So you've got optical spin readout. So it's very attractive. It's a relatively simple system to initialize and read out. And that's certainly been one of the attractions of it in the early days. From an engineering point of view, actually, I simplified it, but it is that. It's a green light source. It's an RF source. It's a clever piece of diamond, and it's a silicon detector. So the activation barrier to start making progress is relatively low. You don't need sophisticated cryogenics. You don't need all sorts of fancy, expensive lasers. You can start. But you can also see the challenge here, because it's lots of discrete components. And ultimately, we need that integrated if you're going to ever come up with a low-cost final solution. Little video here. This is from Jorg, actually, many years ago, actually showing the contrast. I'm actually not sure it's actually running. I will ignore the video, but it actually shows it on-off state just with a simple camera, which is amazing. The fact you can read this quantum state out without any sophisticated optics. Material scientist guys like me, we have to worry about those NVs going into the material, but we also want to worry about all the other defects that might be going in and minimizing those impact, things like strain, dislocations, isotopic enrichment, and also all that bundle of material parameters that we've been working on over the last 10 years with academic partners and increasingly industry. So partly because the appeal of it and that some beautiful work been done across academia and industry means that these color centers in diamond have been explored for a very wide range of quantum applications. So I'm going to give one more example of bulk magnetometry before talking a little bit about quantum networking. But people are looking at wide field magnetometry for bioimaging. There's nanoscale imaging, some nice startups, Kusaba and Kunami in Europe, are using these single NV defects to image things on the nanoscale. So using the diamond, but also developing processing techniques so you can have an atomic size tip to give you atomic size resolution for nanoscale AFM type imaging of magnetic fields. You can actually, the way the transition levels work, they can be sensitive to temperature, which can be a problem in some cases, not in others. So you can actually use that and actually use it as a temperature sensor. Some work recently showed you can actually invert this and actually use it as a room temperature maser. So actually stimulate emission of microwave energy and quantum networking. And I'm proud to say that we've been part of a lot of these projects and applications. That's really exciting. Also is part of the challenge, because how does a company like us work out which one we should be working on more than others, because we have a relatively small team. And of course, you want to maximize your return in industry and have a balanced portfolio of risk. So perhaps not surprisingly, in the last few years, most of our energy and effort have been in the magnetic sensing area, because the perception is, at least for us, some of those markets are a bit closer. In the quantum networking area, we've been trying to facilitate and be part of several academic programs, so we understand the challenges and the risks and what might be needed as that matures. Another area that we've had to work on with the quantum networking and the magnetometry is strain. So this gives you, I'll give you two quick examples of where we've had to worry about material properties. So in a perfect world, you'd like a perfect piece of diamond with a single quantum spin that you can engineer and manipulate and read out. The reality is the material is not quite that ideal. There's strain in the material is associated with the way it's grown. And here on the left, we've had to develop technologies to quantify that strain. So this is a false color map of birefringence, if you like. And here you see we've actually mapped out T2. And actually here you can see in a high strain region, the T2 is lower than in a less strain region. So a lot of work over the last couple of years has been actually working out how to reduce, on average, the strain in the material. The benefit for magnetic sensing, it pushes T2 up, and sensitivity is directly linked to T2 or the square root of T2. In quantum networking, when you want identical photons, you want all those photons to come out at the same frequency, not at slightly different frequencies, because there's local strain in the material that leads to frequency shifts. So that's been important in magnetometry, and I suspect will be increasingly important in the quantum networking world. Just to give you a sense of the type of development work we've had to do, develop QC controls, addressing new markets and new problems meant developing new materials, but actually also developing techniques to quantify the diamond in a metric that's relevant to the end customer or the end partner, and actually put that back into routine development work. So here's just a very simple one. In nitrogen-vacancy work, you care about the level of nitrogen. So can we grow diamond consistently across many runs and within runs with the same level of nitrogen? Because that's only the start of it. You want nitrogen vacancy defects, and typically these are produced by irradiation and annealing techniques. So again, here's some nice work on the right, and these measurements are across many samples across 2 years of different trials. So the fact that the sample at the end is pretty similar to the sample at the beginning means at least over that 2-year period, we've managed to repeat what we did 2 years ago and actually get the same result 2 years later. So that's helped, but this has very much been a heavy focus for the last 2 or 3 years to try and make sure that there's a baseline capability material that the community can rely on and use as a starting point, even though if in the end we might need to improve further. One application we've been working on is, as I said, magnetic sensing. Here's a program that's been relatively public and eventually went public about 18 months ago, where we've been working with Lockheed Martin. Perhaps not surprisingly, the defense industry are interested in things happening under the water. and it's not easy to use EM underwater. So magnetic fields are one of the few things that can penetrate long distances underwater. And secondly, navigation. We all know the GPS signal at ground is very weak and very easy to screen. So actually, GPS denied navigation is a hot topic in the defense world. So developing magnetic sensors with relatively small size, weight, and power potentially gives capability for navigating. Important for defense, but also potentially important for civilian applications, especially if you think about you want your Amazon delivery to land on your doorstep, not in the middle of the road. GPS will get it to roughly within the middle of the road, but if there's a drone coming to your door, how does it know it's going to actually drop that at your door and not your neighbor's door, or worse still, in the middle of the road outside your house? Picture one of the demos that we've worked with Lockheed. Size, weight, and power, the big driver for them. So this whole thing works at less than 5 watts system. Quantum networking, and I apologize, I know this workshop's mainly about quantum networking, but I thought I'd talk about the other to give you a flavor of how some of that feeds into this. Some beautiful work been done both in the US and in Europe, and you heard some of it from Jörg within the German consortium just before lunch. Probably the most recent spectacular work was out the Delft group. It was published in Nature 2 weeks ago, where we think it's the first time we basically achieved entanglement on demand within 3 separate quantum nodes. And it's just as Jörg illustrated, using the nuclear spin as a resource. So basically you can entangle Bob with Alice, write that entanglement state to Bob, he acts as a memory, and then you can go and then start Bob to talk to Charlie. And then come back and interrogate the nuclear spin again. One of the challenges of that was some of the beauty of the work that Delft have done is that challenge of, like, when you want to start using this electronic spin again, not to end up having an impact on that nuclear spin. That nuclear spin is relatively isolated from the environment because it's nuclear spin, so the Bohr magnetron is a couple of thousand times smaller, but nevertheless, it has an influence, and there's many tricks and protocols that the community have developed over the last few years. So really beautiful experiment, and demonstrating principle 3 nodes entangled at the same time, and of those 3 nodes, any other 2 could be entangled as well. And hopefully the basis of more exciting work coming forward. Okay, so quick switch. So the last 5 minutes thinking about commercial. So this is very, very simplistic. It's a very linear, dumb value chain. So here on the left, you've got the material guys, the guys making the heart, the quantum node, the quantum system, the quantum material, whether it be a superconducting circuit or whether it be an atom trapped in a quartz tube. In my case, it's a lump of diamond with NVs or silicon vacancies trapped into it. And then at the end, you've got the classic guys, the system integrators, the guys deploying and selling data effectively to the network, whoever they might be. They might be the defense giant, they might be the Deutsche Telekom, but that's an example of that. And then you've got all these guys in the middle adding value, and then in parallel with that, you've got all sorts of other companies supporting that value chain. The first thing is a very obvious thing. For new technology to come through, that value chain has to work for everybody. And to give you a simple example of the world that I live in the materials business, and we've got a few examples of this where the diamond has helped enable $1 billion industry. So at the system level, it's created billions of dollars of value. The material value it creates is a few $1 million. So that's good. So for material companies like us, a few $1 million is good. But if you come to us and say, look, we want you to start a 5 to 10 year research program to develop this thing that may or may not happen with these risks, then actually that's a tough value proposition. And we need to find a way of de-risking that. And there's different ways. I mean, typically what we do in our most successful programs is typically we will try and make sure that this end guy, this end woman, who's got the real value creation, and see if they really care. Do they really care enough to pull this technology through? Because if they care enough, the likelihood that they've got enough to win, they might pull the stuff through. If that guy isn't there or is not certain, then it's a very risky technology push. And companies always hate that technology push. 9 times out of 10 fail. So you're looking for that pull. I think in quantum, I think we're very fortunate in the sense that with all the government initiatives around, there is actually quite a big consensus pushing, but also that consensus is actually pushing those end industries to say, look, if you're going to stay competitive, you need to be careful of disruption. So be part of that disruption rather than waiting for third party to come and disrupt. And you see a lot of the government initiatives doing that. But that can be a challenge getting that funding model to work, because for material, the work that I've just talked about very, very quickly, for us, it's been a 10-year program, multi-engineer level. So that's cost multiple millions of dollars to do that work, and you've got to be fairly confident you got some return. So that's one challenge, and that's true for me as much as it's true for anybody in the middle of the chain or somebody in parallel with the chain. The other thing that is really, from the time I spent in the US, the US always use, and other places do as well, Europe does as well, but it's really ingrained the idea of having a roadmap. And the concept of having a roadmap takes risk away. Industry hates risk. Everybody hates risk. So having an industry roadmap that says this may or may not, could happen on this type of timescale, and these are the things that need to be done, and then a consensus about that. So it's not just somebody like me saying it, but there's the community saying that for industry helps reduce that risk. And technology in quantum, at least I've been involved in the UK government program, it's all been talked about what it enables, our roadmaps, but actually the roadmap needs to go beyond that. It needs to talk about the technology components and making sure they're there. And some of these government initiatives you've seen have been smart to that. I don't know the details of the German networks out there, but I know the French system recently have made a big point of putting 400 or 500 million aside just for those component bits to come through. So that's going to be important to think through this community. So for guys like us, moving away from you're a customer, we're a material supplier, we sell you a bit of diamond. If this is going to work, we've got to somehow really create a quantum ecosystem where customers and suppliers actually are all part of the same thing, and we solve each other's problems together. And some of those are literally just financial problems. It's how do we make sure there's enough return for this little supplier who's got some key part of the technology, whether it be a laser or a lump of diamond or whatever, actually can make money and make sure it's there. And I think that's an area where Europe has a real strength and can differentiate itself over the likes of the US. The US will invest in something if they see $1 billion. Europe has done a fantastic job of creating lots of $10 to $100 million euro companies delivering niche specialist technology. When the US looks at Europe, they're very envious of that. And that's a strength. We've managed to make those businesses work. And I think for quantum to work, that's something that we need to continue to work on. Last 2 slides, couple of small things about scaling. And again, a learning point, because some of you guys working on diamond 2 or 3 years ago were struggling to get your hands on diamond. And it was a simple thing. We were surprised by the demand. We weren't ready, and it wasn't in production, so you rely on R&D guys to pull it through. So we've invested in more capacity, and to give you an idea, we've just built this large factory that cost us $100 million in capital, and from beginning of that factory to the end was roughly 5 years. Now, having done it once, we probably could do the next one in 3 years, but it's not in any time less than 3 years. So volume requires thinking quite a long time ahead. The other thing, increasingly in our R&D programs, most of you guys who've worked on diamond in the past, that diamond probably would have been in touch with mechanical, single operator polishing. That's not consistent with scale. So increasingly, as you've heard from other talks, working with classical semiconductor processes like plasma systems with Oxford Instruments to actually develop processes that can be scaled at wafer level and not discrete. So my time is up. Hopefully, I've managed to cover CVD as a powerful and potentially very unique material quantum technologies with some of those fundamental things, long adherence times and such like. There's been some really beautiful milestone results in the sensing, but also in the networking community, which really excite me. Commercial progress will really require this ecosystem to be developed and really make sure everybody makes money doing it. roadmaps are can be an effective tool. So with that, I'd like to say thank you for everybody, and thank you to the very many collaborators on this over the years.
Okay. Yes, thank you for the talk. Let's start maybe with a general question. What do you think will be the first use case for entangled-assisted communication networks?
I mean, first thing, the consumer is not going to pay for security. So the consumer it's got to be cheaper, faster, better. So I can't see the consumer caring about security. So I think that the concept of doing something you can't do today, so a network of quantum sensors networked together, I think that's an interesting thing you can't do with classical systems today. I think that one pushback on that with QKD, with the government level of interest, that there is likely to be, I think, defense pull through for QKD. So QKD might well come through earlier than would have been from a commercial point of view because of defense reasons.
Yes, and then yes, reaching this QKD, this use case, what is the current main challenge in your field?
So I think the work in the last 10 years on the materials and manipulating the spin physics has been lovely, and you all gave us some beautiful demonstration of how you can really manipulate these spins. There's still that challenge between integrating those spins and the photonic circuits. So in its crudest sense, it's the integration, and we've got to lower the activation barrier to make the diamond solution more easily compatible with the networks and the solutions already out there. If we can do that, then there's great hope.
Mm-hmm.